In this video, I want to introduce the idea of area of the polar curves that we started talking about today in class. Okay, so go ahead and put that in your table of contents. This is standard I-5, area of a region using an integral, and this is on page 231. You pick this up in class. The target for today is students will determine the area bounded by a polar curve using the integration formula to determine the accumulation. And what we're going to do in this video is kind of derive that formula based on what we've done in the past and what we know. Okay. So let's go ahead and look at that whole curve right there. I'm going to enlarge it really quickly. Okay. So in geometry, I know that's a while back, but in geometry, you actually learn how to find the area of a sector. Hold on one quick. Let me get some color in here. Okay. I think I'm up and running now. So we learn how to find the area of a sector. And when we did this, we actually found it off of a circle. Okay. So if we had a circle, and don't make fun of my circle, and we have a radius, we could find the area of this section of our graph using a formula that was derived in geometry. And that formula is actually the area equals 1/2 the radius squared times the angle involved in that sector. Okay, where the angle within that central angle right there. That's marked. Okay, so I'm going to kind of use the same idea because in my polar curves are circular in nature just because the way a polar graph works, but they aren't perfect circles. But if I could make them be a perfect circle, let me see if I can draw. Oh, that's a terrible line. Again, don't make fun of me. Let's see if I can do that better. Let's get a thicker pen. Maybe that would help. Okay. If I drew a line and made it a circle, I could then approximate that area. Okay, I can already tell that this is a bad approximation just because we have a lot of area here, that area right there, that area right there. This is definitely going to be an over approximation. But if I take what we've done in the past, and that's not looking at one particular problem, but splitting it up into different parts. Let me get, this one's going to require a thinner one. If I actually partition this from the pole, maybe partition it many times, and look at specifically maybe one, and see if connecting those 2 points, I get more of a circular type. So the smaller the partitions, the more circular it's going to be just because of the nature of a polar graph. So if I find this area of a single one, and then find the area of each one of those using that formula right here, then I can add up all of those formulas or all those values and estimate the actual sum of the actual area that I want. Now hopefully that sounds familiar. We've done this a couple of times. Once when we talked about Riemann sums, and then two, we kind of came back here when we talked about arc length and kind of did the same thing. Now, because our polar functions are in terms of r and theta, okay, remember r is the length from the vertex, or sorry, from the origin or the pole to the actual function itself. So from there to there. Sorry, getting an eraser. From there to there. Okay, that would be our r. And if we look at this value in between the measurement in here, we can look at that as our change in theta. Okay. I know from Riemann sums, real quickly, you don't have to write this. Okay, I know if I take the sum of a function times the change of x, that's going to estimate the integral from start to finish of that same function with respect to x. Okay, we learned that in Riemann sums. So, but my function is not in terms of f, it's in terms of r, so I'm going to use that. And it's in terms of theta. But our formula itself is in terms of theta. So, but if we look at that formula and kind of transform it to be just like this equation, or to look something similar to that equation, then I have an integral I can work with. Okay, so that's what I'm going to do. That's kind of, I'm going to take a formula we learned in geometry and just kind of rewrite it to give us something that we can use in calculus. Okay, so I know if I take the sum, okay, of my function, well, 1/2, okay, that 1/2 is part there, but that 1/2 is a coefficient. So remember, coefficients don't really do anything. We kind of just bring them along for a process and then use them when we need to. Okay, my function is already in terms of r, or my polar graph or my polar equation is already in terms of r, so that works. And now the theta in my formula, remember I'm referring to this formula right here, I can replace that with my change in theta. And then it looks very, very similar to my Riemann sum, which means this can actually approximate the integral of 1/2 my polar equation, r squared, and d theta. Okay, so we're taking an integral with respect to theta. Now, we usually put an a and a b as our limits. With polar curves, we don't use a and b, but we use very similar letters, alpha and beta. Okay, and what alpha and beta are, so where alpha, remember Greek letters, and beta are going to be the angles that bound our region. Okay, so the formula to find the area of any polar curve, or the area enclosed by our single curve, this is only one curve, of course. To find the area is a very simple formula. It's just the integral from alpha to beta of 1/2 r squared, our r being our polar curve, with respect to theta. Because remember, in class we talked about theta being our our independent variables. So that makes sense that we're taking the integral with respect to that theta. Okay, and that's the variable in our problem. I tend to write mine like this. I like my coefficients out front, so I often pull out the 1/2 and leave the r squared d theta, okay, in there. So that kind of gives us a formula that's specific to polar curves that allows us to find the area. So I'm going to highlight that. Okay, so come in tomorrow, we're going to actually apply this formula and actually find some area and figure out, we're also going to talk about how we find some bounds, kind of what kind of questions could be asked, and then what kind of graphs could be produced. And we spent a little time of that today. Okay, so if you have any questions, come in and see me. Quick and short.